There we go. Okay, I know how this works. It is, what is it? It is September 16th. As I already mentioned, I'm not crazy about how the book does this, the order the book goes in. We're going back to 1.4. We'll call it 1.4b. And we need to talk about the formal definition of what it means to be continuous. You've been dealing with this since Algebra 2. Can you graph the function without picking up your pencil? That is not a super mathematical definition. We want to do better. And now that we've been through what we've been through in this unit, we have the language to talk about exactly what it means to be continuous. Let's say I have some function, and from the left side I'm approaching some value, and from the right side I'm approaching some value, and that happens to equal the value that I have right there. We're continuous, right, at that point? For a function to be continuous at a particular value, three things must all A, be defined, and B, be equal for us to be continuous. For a function to be continuous at x equals c, at x equals c, what I'm approaching from the left has to equal what I'm approaching from the right, has to equal the value of the function right there. The limits as x approaches c from the left of f of x must equal f of c. Notice not f of x, but f at that particular c value must equal the limit as x approaches c from the right of f of x. And actually, I feel like I want to say just a little more. They all have to be equal, but also they have to all be defined. If any of these don't exist or are undefined, you can't say you're continuous there. All three must be defined and equal. And I feel like the definition should make sense. What you're approaching from the left equals from the right equals the value right there. Sometimes, though, it's going to make more sense to use a slightly different definition. If I don't really know about left-right things, I just know about an overall limit. Doesn't the limit just have to equal the f value right there? Can't we also say that? Or we can say the limit as x approaches c of f of x equals f of c. Doing with that. Depending on how the function was given, that definition might also make sense to us. But for this thing to exist, the limit from the left has to equal the limit from the right, and then everything's all good. So the first thing we're going to need to be able to do is explain why particular functions are or are not continuous. And on the first day when I mentioned everything in here we deal with graphically, numerically, analytically, and verbally, this is kind of the verbally stuff. Can we explain using proper language, but also proper notation, why something is not continuous? Our reasons are not going to be things like, oh, there's a hole, there's a jump, there's a whatever. I want to go and try to use this definition to be mathematically precise about why we're not continuous. So let me show you three examples. For our first one, I would like to take a look at a function that looks like this. I hope you'd agree that we're not continuous at x equals c. Right? Not continuous, there's that hole there, but that's not quite going to be good enough for an explanation. We're not continuous at x equals c because. All three of these things must be defined and they have to be equal. So what's wrong? Bennett. Yeah, but I actually have a little bit of an issue with that. First of all, looks like I'm approaching something from the left, from the right. What is f of c? Undefined. It's not okay to say something like undefined doesn't equal 3. So really, how should I describe my issue? I feel like I actually just sort of said something like that. Be more specific. Which one? That's what I want for the explanation. What problem do we have here? Because f of c is not defined or is undefined. That would work. And I actually I'm actually really glad you said that, Bennett, because most people will say that on a quiz, and I'm going to be picky and not give you credit for something like that, because again, it's like saying 3 doesn't equal undefined. It's perfectly fine to say 3 doesn't equal 2. Not okay to say 3 doesn't equal undefined. What's my issue? The issue is f of c is not defined. Okay, well, what if we look at something like this? One of these. F of c is now going to be defined. It's good. And I've got a graph like that. And again, I hope you can just look at this and realize we're not continuous. At x equals c, because Tyler. There's a jump, but again, let's try to use our definition somehow to describe what exactly is the problem. What part of that definition isn't holding? Do you want to give it a try? Sophie? That's what I want. Do they both exist? Sure they do. My issue here is the limit as x approaches c from the left of f of x does not equal the limit as x approaches c from the right of f of x. That's my precise reason for the problem. Absolutely there's a jump, but this is the formal reason why we're not continuous. By the way, I feel like this is how the homework's going to start out with some graphs, and you tell me what the problem is.
So according to the second formula, the limit is the overall limit equals that. Can you just say that the overall limit?
I guess what I'd really prefer, though, is why does it not exist? For this reason over here. So I really would prefer something like that. I feel like my next example, though, is going to be why I have that other part of the definition. Bless you. Let's take a look at one of these. Let's do this and that. Oh, you know what? I should probably fill these in, and I'll do something like that. I hope you agree I'm not continuous. There's a hole. What's my problem? Olivia. Yeah, we can definitely say f of c doesn't equal this limit. F of c doesn't equal that limit. Could you make this any more general? Is there any other way we can say that would kind of take care of both of those issues that you mentioned in like one statement? What am I going for? That's kind of why I gave you this one. They both are defined, they both exist, but no, the overall limit doesn't equal f of c. The limit as x approaches c of f of x does not equal f of c. When this stuff shows up on a quiz eventually, I am going to be pretty picky with your notation. I mentioned this before, but I'm not okay with like limit as x approaches c doesn't equal f of c. There's got to be something inside your limit, right? I'm also not okay with you writing that last one as the limit as x approaches c of f of x does not equal f of x. What's wrong with that? That's the same thing that I wrote, isn't it? What's different? This is the function in general. That's not what I'm talking about. I'm talking about at that particular x value. I'm going to be picky about this stuff. And we just have to make sure we know what's going on. Do you understand the notation here? Are there any questions about notation? I still feel like this unit is the ugliest in terms of notation, just getting it precise. Okay. We're discontinuous at all those places. Next thing. There are two different types of discontinuities that we're going to talk about. Actually, you know there's three. There's holes, vertical asymptotes, jumps, all those things. But I can actually kind of group the three into two main issues. And we're going to call those two different types of discontinuities either removable discontinuities or non-removable discontinuities. So, two types of discontinuities first is called a removable discontinuity. And that's actually just a fancy name for a hole. The AP exam will use them interchangeably, so we do need to know the language. And the idea is, if we have a removable discontinuity, we can sort of patch that discontinuity, kind of fill it in, or redefine our function right there to make our function continuous. It can be, I'll say, kind of patched. Is that how we spell it? We'll go with that. Or really redefined at x equals c to make it continuous. We can change just one value on our graph, and suddenly our graph will become continuous. Let me go back for a moment. Over here, I would call this a removable discontinuity because I could change just 1 point on my graph, like fill this in, and I'm suddenly continuous. Would this one be a removable discontinuity? Sure, we could change this filled in dot, just kind of move it down, we're good. How about this one? Can you change 1 point to make this one good? You'd have to like change the whole thing to kind of bring it, that's changing a whole bunch of points. That's not going to be removable. Our better definition of a removable discontinuity is our limit as x approaches c exists. So f of c can be redefined there to equal that limit. We're going to say the limit as x approaches c of f of x exists. But either doesn't equal f of c or f of c is undefined. I already mentioned the other name. The other type is a non-removable discontinuity. Those are going to be jumps or vertical asymptotes. More with that in a moment. Non-removable discontinuity. For our purposes, jumps or vertical asymptotes. They can't be fixed just at 1 point. You'd have to like change a whole bunch of points to make it continuous. And really what you're going to look for is your overall limit is not going to exist there. The limit as x approaches c of your function does not exist. And I feel like I need to give you a moment or two to do some writing. Yeah?
What if we saw some functions where the two sides of the limit were approaching infinity? But that would still be a vertical asymptote, would it?
Yes, and I'll explain how this is still okay. And I'm realizing I'm just covering up other things that some of you are writing. I'll move in just a second. Yeah, there's a vertical asymptote. You'd say your limit's infinity. But when I taught you that stuff yesterday, I said that all these limits still don't exist. It's just a better way of describing not existing. So it still does not exist, that limit. Does anyone... Yes. Is anyone still writing what's on the screen? That's not what you're writing. Okay. So let's talk about finding these things. By the time we're done with class, I need to be able to give you a function. You need to be able to tell me a formula for a function. You need to be able to tell me where we're discontinuous and classify those discontinuities as removable or non-removable. So, there are two places we are going to focus on trying to find these discontinuities. Discontinuities can occur. Discontinuities can occur either where the denominator equals 0. We know I already dealt with a few of those. Where the denominator equals 0, or if we have a piecewise function where you move from one piece to the other. Or, how do I want to say this exactly? How about I call it at the end of a piece of a piecewise function? At the end of a piece of a piecewise function. Okay. Let's start by dealing with the denominator issue. Number one, when the denominator equals 0. We kind of dealt with a little bit of that yesterday with our vertical asymptotes, but I feel like I gave you an example where the denominator was 0, but it wasn't a vertical asymptote because it was a whole. Rather than going through our whole limit process with these things, here's a kind of the shortcut we can use for figuring out if in the denominator, if that place is a removable discontinuity or non-removable discontinuity. If the problem cancels, it's removable. If we've removed our problem, it's removable. It's a whole. If the problem cancels, it's removable. There's a hole. If the problem remains, and this means after simplifying, of course, if the problem remains, it's non-removable, and specifically, it'll be a vertical asymptote. We can't really get jumps from just issues like that. If the problem remains, it's non-removable. Which is a vertical asymptote. And I'd like you to copy down the example f of x equals x squared minus 9 over x squared plus 5x plus 6. I want to find where this thing is discontinuous and then classify those as removable or non-removable. And I'm thinking in a moment if I can get this printed, then I don't have to stop the camera and just stick things under there. Multitasking. What obviously should the first thing be that you do with a function like this? I feel like this should be pretty natural.
Factor.
Do it. Go factor that thing, top and bottom. Don't simplify yet. X plus 3, x minus 3, x plus 3, x plus 2. Obviously, the factoring can get harder, but this will be fine for an example. At this point, we stop, and we talk about where we're discontinuous. We're going to look at our denominator, x equals negative 3 and negative 2. Those are our two discontinuities. I'll classify them in a moment, but they both count as places where I'm discontinuous. I'm going to simplify the x plus 3's cancel. X minus 3 over x plus 2. By the time I've simplified, do I still have an issue at x equals negative 3 in my denominator? Or did I completely remove that problem? That's not really why the name is that, but it's kind of nice. Did I remove that problem? Sure. That problem is gone. I'm going to call this thing removable. Do you still have a problem at x equals negative 2? You do. That makes that one non-removable. And I don't have a graph of this ready to go, but if we looked at a graph of this, there would be a vertical asymptote at x equals negative 2 and a hole at x equals negative 3. Do you follow how to do this? I feel like there are a couple in the homework that are much longer than this, but already factored for you, so you can kind of look, okay, I'm going to completely cancel this issue, removable. This one remains a little bit. That makes it non-removable. If it remains at all, even if you cancel like, you know what, I'm not going to say anything else. You're going to see that in the homework, and we'll talk about it next time. One more of these. Places where the denominator is 0. So f of x equals cosine of x. What's going to make the denominator 0? Actually, first let's... Oh, wait a minute. Can you rewrite this? So there's a denominator.
1 over secant.
That's going to make it worse. I don't like secants. There's no denominator, right?
Oh.
What makes the denominator equal 0? There's no denominator. So where is this thing discontinuous? You know what this looks like, right? Can you trace out an entire cosine without picking up your pencil? Sure. Oh, sure. Thank you. And I guess I'm picking up my pencil just to go the other direction, but can't you trace it without picking up your pencil? You're going to see things like this from time to time in the homework. Where are we discontinuous? No, nowhere. You're just going to say something like this is either continuous everywhere, or you'll say there are no discontinuities. Don't be thrown by something like this. There are two things you're looking for. You're looking for denominators. None of those there. And you're looking at the end of a piece of a piecewise, that's not a piecewise function, even though I haven't taught you that stuff yet. So you're continuous. Anything here? Can you raise your hand if you're still writing anything on the screen? Because if not, I'm going to turn the page. Yes, you're still going. Anyone? Okay, I do want to start a fresh page here. Our other case is just a little subtler, I think. Second case is when we jump from the end of one piece of a piecewise function to another piece of a piecewise function. We're going to call this at the end of a piece of a piecewise function. we know what a piecewise, we've looked at them, we've called them piecewise functions, right? Good where you're greater than 0, good, okay, all those things. There are three things that could happen here. We could have this case. If at a particular x value, the limit as x approaches c from the left of my function might equal f of c, might equal the limit as x approaches c from the right of my function. I could have that happening when I go from one piece to another, which means I'm approaching something from the left, which is the same as the value right there, which is the same as what I'm approaching from the right. Is that a removable or a non-removable discontinuity? Or should I not even be asking that question? What do I have going on here? Is this a non-removable discontinuity, a removable discontinuity, some other thing? We're perfectly continuous. These are places we could have a discontinuity, but maybe we won't. Something like this, it's continuous there. If all three things are equal, that's our definition of being continuous. We could have something like this. If the limit as x approaches c from the left of f of x exists, but doesn't equal the limit as x approaches c from the right of f of x. I'm approaching something else. Am I actually discontinuous there? Yeah. How? Removable? You can fix it. Non-removable? You can't. Tyler? Non-removable. It has a non-removable discontinuity there. And specifically, what is it? It's jump. There's one more thing that could happen when I go from one piece to another piece. If the limit as x approaches c of my function doesn't equal f of c. I've got a limit that I'm approaching, but that's not the same as my value there. Discontinuous or continuous? Discontinuous. How? Removable or non-removable?
Removable.
You can fix it at that one point and things are good. It has a removable discontinuity there. And again, in this case, it's a hole. I've got to show you a few examples of this, just because I feel like we need to see some specific uses of this. I'd like to take a look at f of x equals the piecewise function x plus 1 when x is less than or equal to 0, x squared plus 1 when x is greater than 0. I want to figure out where we're discontinuous and if that discontinuity is removable or non-removable. Well, there are two things I should be on the lookout for. Denominators, doesn't matter. At the end of a piece of a piecewise function, I have that here. I'm switching pieces at x equals 0. I don't actually know if I'm discontinuous yet because remember that first situation where it could be perfectly continuous. So I'm just going to say there is a possible discontinuity at x equals 0. I might be discontinuous there. Not totally sure. Well, you've noticed that these are like involving, well, actually, these are all involving kind of checking our definition of continuity, checking our limit from the left, our limit from the right, our value there. We need to go, and on 3 separate lines, we need to check those 3 things, and then based on what we get, reach some sort of conclusion. We need to go do the limit as x approaches 0 from the left of the function. We need to go do the limit as x approaches 0 from the right of the function. And we need to go do f of 0. And I feel like none of that is anything new. We've done this. You go do it. Then when you're done, we'll reach a conclusion. From the left? From the left, 1. 0 plus 1, 1. From the right, 1. Not because it's 0 plus 1, but because it's 0 squared plus 1, and that's 1. F of 0? What type of discontinuity do we have? We don't. We're perfectly continuous. We're approaching 1. We're approaching 1. We equal 1 right there. What are we going to say here? We're continuous everywhere. There was only one place I could have had an issue, x equals 0, and I just proved, no, we're totally good. Continuous everywhere. There you go. That's what we're looking at. It's piecewise function, but it's continuous. You can trace the whole thing out without picking up your pencil. Do you get, though, the check that we're looking for? We're looking at those 3 things. Continuous everywhere, I guess we'll say because we're continuous at x equals 0. And how do I know I'm continuous at x equals 0? Because the limit as x approaches 0 from the left of f of x equals f of 0 equals the limit of as x approaches 0 from the right of f of x. If they would ever ask you on the AP exam, are we continuous there? Justify your answer. That's your justification. Really just going back to our definition of what it means to be continuous. I think I want to give you another one that you're going to try, and we'll see what we can do with this. Then I think we'll do one last final quick thing, and then we'll be good for today. Okay, you are going to deal with a more interesting function. I would like you to deal with f of x equals, I'm going to give you 4 pieces here. X squared plus 2, where x is less than or equal to 2. 3x minus 1, when x is between 2 and 3. 5, right when x equals 3. And 14 minus 2x, when x is greater than 3. Can you very quickly tell me where we could be discontinuous? Don't think super hard. 2 and 3. You see that? Go do your checks at x equals 2 and x equals 3. Do your limit from the left, the limit from the right, the value there, and then reach a conclusion. Right now, though, I'm just going to say possible discontinuities. At x equals 2 and x equals 3. Make sure when you're writing these things out, you're still using good notation. Limit as x approaches 2 from the left of f of x. There's got to be that f of x inside there. This actually tends to be the quiz on this stuff where I really nail people on the notation because they're forgetting the f's inside the little things. And honestly, to remember like what type of discontinuity is, I find it helpful to try to draw a little graph. I'm approaching this thing, I'm approaching that thing, the value's there. What happened when I tried to put those pieces together? When you are done, make sure your notation is looking like mine. Ehit, what did you say for the limit as we approach 2 from the left of f of x?
6.
Yes, right. 2 squared plus 2, 4 plus 2, we're getting 6. Good. Melissa, what about as we approach 2 from the right? 5. 3 times 2 minus 1, that's 5. And Sora, what about f of 2? 6. And I know you might feel that it's a little redundant to do that since you already did that up here, but I actually really do need to see the plugging in again. You'll see why in a moment with the other problem. I'm already giving something away, but do show all 3 things. Who wants to tell me what's happening at x equals 2? 1, 2. Any new people or quieter people? Okay, you're not new, but I'm going to call on you anyhow. Andrew.
There's a hole, a removable discontinuity.
Good. Removable? Olivia? I'm approaching 6 from the left side. What am I equaling there? I'm equaling 6. What am I approaching from the right side? You know what? I actually don't think I did this in the best way. I probably should have done the limit as we approach 2 from the left, then f of 2, then from the right. May make a little more sense. But yeah, I'm going to say it's a jump, which means what? Removable or non-removable? Non-removable. I've got a non-removable discontinuity at x equals 2. You okay with that?
Yeah.
Yeah, I'm really not crazy about this order. I really should have done the f of 3 in the middle so I kind of see from the left, right there, from the right, whatever. Mahalis, how about as we approach 3 from the left? 3 times 3 minus 1, 8. Ella, what about as we approach 3 from the right of f of x? It's looking good. 14 minus 2 times 3, 14 minus 6, 8. Akash, what about f of 3?
5.
What is this? Tyler. What was that? A hole. I'm approaching 8. I'm approaching 8. But I'm equaling 5 right there. So what are we going to call it? Removable discontinuity. There is a removable discontinuity at x equals 3. Why are we non-removable at x equals 2? Well, really because the limit as x approaches 2 from the left of f of x doesn't equal the limit as x approaches 2 from the right of f of x. Why are we removable here? Well, because the limit as x approaches 3 of f of x, which we didn't find, but we can find, what is that limit? 8 does not equal f of 3. If you are asked to justify things, that's the line I'm looking for. I was going to say it seems like we're being quiet today, but I think we always are. Can you, give me a nod if you're feeling like you're understanding what's going on? And if not, can you please ask me a question or two? Oh, and I do want to show you this. This is a good one. This is a good one. And then I think one last thing, and we'll call it for today. I think I have a little bit too much to do next class, so if we can just tiny bit of that, we'll be okay. By the way, yeah, Non-removable discontinuity at x equals 2, I've got that jump. Removable here, I've got that hole that gets kind of filled in down there. That's what's happening. One last thing we're going to start to take a look at. And at some point I will need to take a break, go to the computer, show you something, restart the recording, I hope, and then finish things off. The AP exam absolutely loves questions like this. Making functions continuous. Am I on the screen? Thank you. Making functions continuous. For example, find the value of a that makes f of x continuous everywhere. And my function f of x is going to equal, let's see, 2x cubed minus 4 when x is greater than or equal to 2, ax plus 2 when x is less than 2. I want to find the particular value of that constant a that will make this thing continuous everywhere. However, I feel like for starters, there is only one possible place I could be discontinuous. Where? 2. That is the only place I'm really going to care about making sure this thing is continuous, because I know I'm going to be good everywhere else. I want to focus on x equals 2. I'm going to take a quick break.